Here we are on the top of the tower, 220 meters, and here you see all the solar field with the 10,600 mirrors, which will be aiming the light of the sun to the top of the receiver, and that is increasing the temperature to 560 degrees Celsius.
A global industrial revolution is underway.
Yes, we have a technological challenge for our environment, for the well-being of the population of the planet, for civilization.
Driven by passionate, dedicated individuals intent on shaping a new world.
I do it because I look at my kids, and I honestly am convinced that this is the way.
A cleaner world.
There is a way forward other than burning fossil fuels out of our funnels.
A greener world.
This wind farm is producing more hours of power into the grid than all wind farms in the UK and probably in the world.
What we've done in the past is not going to solve these challenges. We need to find new ways, and I think the only way to do that is to bravely step forward and implement technology.
Together, they are pushing engineering to its limits. To create extraordinary machines that can protect our planet for the future. We face one of the greatest challenges in the history of humanity. To eliminate the fuels that have driven progress and technology for over a century. While our thirst for energy only grows. Could the solution lie with an ancient and distant power source?
It's without question that in our solar system, the sun is the greatest source of energy. And the better we can take advantage of that, the better it is for us as a civilization.
It's like a nuclear reactor in the sky, and it provides endless power. And if we can harvest just fractions of this, it can power all our consumption.
Giant strides have been made in capturing the sun's energy. But to replace fossil fuels, solar power needs to step up a gear.
We've got a long way to go. The way I see it, we've only got 2% of the world's energy is solar. So there's a massive opportunity there, and this technology is made for it.
Engineers are racing to capture more of the sun's power, to open vast new expanses for solar panels, and even to make solar electricity available through the night.
This is the full cycle that allows us to keep generation 24 hours using 100% only renewable energy, the light from the sun. This is the future.
The vast majority of solar power today is generated by silicon solar panels. These are made of many individual cells. Each cell has two thin layers of crystalline silicon, which have been altered so that one is slightly negatively charged while the other is positive. The magic happens when light falls on it. Electrons in the silicon atoms absorb the energy and break free. The negatively charged electrons are then drawn towards the positive layer. Once connected to a circuit, this flow of electrons becomes electricity. Solar panels like this are on rooftops all over the world, producing clean, green electricity to power our homes and charge our gadgets. But transportation is a much tougher challenge. It's still overwhelmingly powered by fossil fuels. A tech startup in Holland has gone right back to the drawing board, inventing a new car from first principles that could revolutionize personal travel. Their goal is to prevent billions of people buying gas-powered cars by offering them a vehicle that charges itself for free.
Everybody said we couldn't do it, and that's what makes it interesting. So I think that's actually one of the things that motivates us, that it seems like an impossible challenge. And actually, if we look back at the beginning, it all started with the World Solar Challenge.
Their story began at a race across Australia. Every 2 years, a fleet of futuristic vehicles can be seen streaking across the desert. This 1,800-mile race is powered by the sun, with cars built by students from around the world. In 2012, a Dutch team from Eindhoven, including electrical engineering student Arjo van der Ham, decided to enter for the first time.
I think most people were there for the adventure and for actually building something with your own hands during your studies and seeing it work and then trying to win the race in Australia.
In previous years, all entries had been one-seaters, built purely for speed. But that year, the team decided to enter a new category that awarded extra points for comfort and practicality. The idea was to encourage the development of a commercially viable solar-powered car.
We said, okay, let's build a four-seater car. And that became Stella, the world's first solar-powered family car. It was a car that had a flat roof, especially because of the efficiency of the solar panels. Furthermore, it was very aerodynamic, it was very lightweight. It was made almost completely out of carbon fiber.
The team had just over a year to fully design and build a radical new solar car that could also be a practical family vehicle for everyday use. Stella, they hoped, would be the blueprint for the car of the future.
People would be sleeping actually at the university, waking up, build a solar car, go back to sleep for 6 hours, wake up and go build again. So this was really an intense period for most of the people in the team.
On the 6th of October 2013, the only family-sized car in the race crossed the starting line in Darwin, Australia. For the next 6 days, Stella would be racing through the desert, powered by the sun, albeit accompanied by gas-powered support vehicles.
During the race we had the solar car, and then in front of that we had a small van called the strategy van, and was packed with computers, and we had 2 guys, so me and my buddy, modeling and calculating exactly how fast should we drive with the solar car such that at the end of the day our battery is exactly empty.
Everyone expected the comfortable 4-seater to be much slower than the others. But by day 3, she'd hit 75 miles per hour. So fast, the team bus couldn't keep up.
Kijk in de spiegeltjes, zie je het stipje steeds groter worden natuurlijk. Een apart moment als je ingehaald wordt in je eigen zonneauto. Dat was een goed momentje. Ja.
Before long, she'd overtaken their leading competitor, Team Bochum from Germany, despite carrying twice as many people.
Goed die reactie? Holy shit. Ja. Hallo, goed bezig, joh.
But the following day, the car ran into difficulty and needed an emergency pit stop. The team fixed the issues, but they'd lost precious minutes. And on day 5, they lost even more time to their rivals.
Ik heb even getimed ook. Het eerste uur lagen we al 10 minuten achter op Bochum.
By the morning of the final day, the race was still tight. But Arjo had a trick up his sleeve.
En zo laden we nog ongeveer 2 à 3% bij in de batterij. Waarmee we zo meteen weer net wat harder kunnen rijden. Dus qua tijd liggen ze redelijk voorop, maar als we naar de scores kijken, dan gaat het heel close worden tussen Bochum en ons.
Stella crossed the line in Adelaide having driven 1,900 miles in 40 hours, with an average speed of 47 miles per hour, the second fastest in the category. But the cars weren't only judged on speed. they could earn extra points for the number of passengers carried and how it would fare in the real world. And it's here that Stella came into her own.
A jury would take your car and see if they can parallel park it easy. How many suitcases would fit in? Are there any cup holders? How easy is it to get in and get out, etc. And they would score points on that for all the different cars. And then all of these scores combined would make up the final winner of the cruiser class.
With bonus points for real-world credentials, the team squeezed ahead of the competition and took first place with a family-sized car. But they knew that to really make a difference, the hard part was still ahead of them.
But at that point, you're not really changing anything, right? You're just making one car and driving it through the desert of Australia, and there's 5 trucks behind it to carry all the spare parts. So you really have to take the concept to the market to really make an impact and try and improve the planet in that sense.
Ayo and 4 other team members decided to make the dream a reality and launched Lightyear to make solar-powered cars for the public.
In 1 year, the entire fleet of cars throughout the world, they will drive 1 light year worth of kilometers. And the mission of the company is to get that to 1 light year of sustainable kilometers by 2035.
To achieve their mission, they set about turning Stella's outlandish design into something more attractive to consumers, while still keeping the radical approach.
We came up with our own scoring formula, what would make this car better. And the key metric that we optimized the Lightyear 1 for is the amount of miles you can drive each year on the sun. So the amount of miles you can drive for free. And that also guided all the decisions. So if you have to decide whether the car should be a bit wider to accommodate more solar panels or whether it should be a bit smaller to make it more aerodynamic, you calculate how much solar kilometers would option 1 give and how many solar kilometers would option 2 give, and then make your decision. So this is what guided the development of the Lightyear 1.
As Chief Technical Officer, Ayo has overseen the design of the solar panels. At their workshop in the Netherlands, Lightyear are fixing them in place. With panels on the roof and the bonnet, they cover 54 square feet in total. But although they work in the same way as a standard panel, Ayo has altered the structure to maximize the power. A special technique can reveal the design.
We can actually show the structure of the panels and any defects that the panel will have using an EL test. And with an EL test, you actually use the solar panel in reverse. So normally the solar panel would turn sunlight into electricity, but if you actually do it the other way around and you provide the electricity to the panel, it will work as a light source. And it will light up in the infrared spectrum. And now we make it dark in the room, so we turn off the lights. We take a picture with the camera that's modified to actually show up the IR light, and then we can see the groups lighting up. You see all of the cells lighting up, but there's a couple of exceptions. So this is actually an old panel that we used already for a lot of tests and we abused quite a bit. So that's also the places where the solar cells themselves don't work anymore.
Like an X-ray, as well as showing what's broken, the image reveals the inner structure.
So to increase the power output of the solar panel, we've done lots of small tricks, like putting all the solar cells pretty close to the edge. We've cut them to a smaller size, and that way we can place them closer together.
Lightyear claim these are the most efficient solar panels on any car, with the improvements gaining them 20% more power. And as well as squeezing more solar cells into every square foot, Ayo has divided them into groups. To see the benefit of that, you need sunlight. Luckily for countries like Holland, the panels even work on a cloudy day. First, Ayo is connecting this regular solar panel to a voltmeter. This will reveal what impact shadows can have on the power they produce.
So we've connected the panel to the meter, and if I put a shadow on it, you will see this number dropping, and it actually doesn't matter where I put the shadow, you lose the same amount of energy.
If a shadow falls on even one solar cell, the power generated by every other cell drops by the same amount, even if they're in sunlight, because they're all connected. So the whole panel becomes much less efficient. This doesn't matter much for panels on rooftops that rarely have shadows fall on them. But cars regularly drive under trees or past buildings.
On this panel, we've actually divided the panel into 11 very small panels. These 11 very small panels allow us that if one of them is in the shade, one cell, it will only shut down one small group of the panel and not the entire panel. And we can actually demonstrate this. And if I go over it with this board, then I create a shadow on the front, and then only the first meter will show that it actually drops, and the other meters, they still show the same value. And then if I move it along, the value on the first meter actually comes back, and it drops on the second meter. And then if I move even further along, the same thing happens on the third meter. So as I go over the different groups, I will only shut down the performance of that group, and not of the entire roof, which you would see on a regular panel.
As if reinventing the solar panel wasn't enough, the Lightyear team have an even bigger engineering goal: making the car one of the most efficient ever produced.
The Lightyear 1 is designed to maximize the amount of miles you can drive each year on the sun. And if you break that down, then the biggest factor is aerodynamics. So making the car more aerodynamic is where you can save the most on the energy consumption of the car.
Most of the design process happens using computer simulations. But now the team must prove how streamlined the car really is. Annemiek Koers is responsible for Lightyear 1's aerodynamics.
We are currently in the wind tunnel with the prototype of Lightyear 1 to test how it performs at different speeds. So we test the airflow over the car, how much drag does it produce, and what effect that has on the range eventually of the car.
The tests will reveal the drag coefficient, a number that tells you how much wind resistance the car has. The target is to get down to about 0.2, which would equal the most streamlined production car ever made. With such low drag, it could drive much further with the precious solar energy it collects. But compared to a regular car, the team face an extra challenge. As well as being streamlined, the shape must also fit enough panels.
The aerodynamics are a bit constrained by the solar roof. It needs to be quite flat surface on top instead of having very curved surfaces, which would be maybe better for aerodynamics.
But the team have managed to find a profile that boosts both the solar power and efficiency. One that gives a larger area for the panels while also reducing drag.
You can see that we have a very shallow slope going to the rear, and the flow can stay attached over that full length. And if you have a shorter car, we will have a steeper slope, and that will detach the flow and will create a lot of drag.
The team analyzed and modified every inch of the car, replacing bulky wing mirrors with streamlined cameras and fixing covers over the back wheels. Eventually, the team get the drag coefficient down even further than they'd hoped, below 0.2.
So we can claim to be the most efficient production car by the time we get to production, but that's of course the first step.
This world-beating efficiency means the solar energy can go much further, even in cool, cloudy countries.
The solar panel will actually give you enough energy to drive somewhere around 8,000 kilometers per year in the Netherlands. It doesn't sound like that much, right? 8,000 kilometers. But the average car in the Netherlands actually drives only 11,000. For California, they drive much more, but there's also much more sunlight, so you get again around 70% of your annual energy need you get from the solar panel.
For the other 30%, the Lightyear 1 can be plugged in and charged like a regular electric car. For now, to pre-order one will set you back well over $100,000. But it could also save thousands at the pump.
Towards the future, we will be developing an affordable version of the Lightyear One, and we see energy efficiency is the key to the price in the longer term.
But while solar cars may still have a premium price tag, the cost of standard solar panels has already plummeted. The main mineral used to make solar panels, quartz, is abundant and cheap. And by mass manufacturing in large factories with automated production lines, they also cost less to make.
Solar power now is the most affordable source of power. It's just a matter of capturing this energy. And solar power now beats coal-fired power, diesel generators, and now hundreds of millions of the solar panels are manufactured every year.
With such cheap panels available, solar farms have mushroomed. Many are so large, they're visible from space. Some generate over 2 gigawatts of electricity, enough to charge 400 million phones at the same time. And yet solar power still produces only 2% of the world's electricity. That's because although panels are cheap, they need the right kind of location.
So one of the challenges, and this is now starting to happen with the very high number of solar panels, we are searching for new places to put them. And it's a quest to find these areas in good positions.
As solar farms get bigger, they start to compete with other uses for the land, such as recreation, farming, forests, and other wildlife habitats.
It's questionable whether to set aside big surfaces for the solar farms. And it's becoming more and more difficult to find good spots for at least very large solar plants.
To solve this conundrum, an entirely different approach is starting to make waves. Børge Bjørneklært is the founder of Ocean Sun, a company making platforms for solar panels that float. Børge realized that there are water bodies all over the world with readily available sunlit surfaces. Many, like the Magat Reservoir in the Philippines, are next to hydropower dams, which has a big benefit.
One very nice thing about combining floating solar power and the hydroelectric power is the very short distance from producing solar power to delivering it out to the grid, because the infrastructure is already in place at the power station.
The solar panels generate electricity when it's sunny, while the dam makes power when it rains.
It has the flexibility over the seasons. For the rainy season and the dry seasons, you can make a more steady power production. So this combination is a fantastic application.
Other companies are also targeting lakes and reservoirs. But Børge has set his sights on a much bigger body of water, the sea. The main obstacle is the ocean waves.
The challenge is very much to create a protective environment for these solar panels, and also to cope with waves and also strong winds that can occur on water surfaces.
Ocean Sun tested their design off Norway's coast. The most critical piece of engineering that protects the panels is also the simplest: the thin polyethylene membrane that forms the surface.
This is the fabric of our system, which we place the solar panels on top. As you can see, it's less than 1 millimeter thick.
It interacts with the surface tension of the water to create two curious and powerful effects. Firstly, it boosts the strength of the material.
This fantastic effect that this layer has when we put it on top, and it came to us as a big surprise. that you could actually walk around on the water surface through this very thin fabric.
And secondly, Borge discovered that the membrane changes how water behaves.
It has a dampening effect on the motion of the waves, and it serves as an ideal surface for placing solar power on top of it.
In January 2019, the floating system had a chance to prove itself.
In the winter, we had a pretty bad storm coming in over Norway. Bridges were closed and the ferries stopped, and we really got to test our system in quite bad conditions.
The floating solar array was hit by high winds and waves. Once the storm had blown over, the panels emerged unscathed and still generating power. Having proved it can survive harsh ocean conditions, sea-based solar seems perfectly placed for an energy revolution, as nearly half the world's population lives near the coast.
Many big cities, like here in Oslo, have the ocean right on their doorstep. And if we can use the surfaces here for floating solar power, you have a very short transmission to the consumers.
Research is underway to minimize any negative impact on marine life. So far, results have shown that floating panels appear to reduce damaging algae blooms. With water surfaces now available as well as land, experts estimate that 70,000 new solar panels are being laid every hour, equivalent to 1,000 soccer fields a day. But although solar is already the world's fastest growing energy technology, it could be generating even more power. Standard solar cells can only convert about 1/5 of the energy that's available in sunlight into electricity.
The fundamental problem with your standard solar panel is it captures the little bit for electricity, 15 to 20%, and throws the rest away.
If that percentage were increased, we could accelerate the transition to clean energy sources. In Victoria, Australia, a company called Regen think they have found a way to harness more of the sun's power. Inventor John Lassick came up with part of the solution as a student way back in 1975.
I was pretty ambitious for a young lad, and I thought if you're going to make perhaps a quarter or even half of the world's energy from solar energy, you have to have something that is highly efficient and very, very powerful.
In the 1970s, solar panels were small and even less efficient than they are today. But John had a simple idea how to supercharge them. He calculated that a parabolic dish with a reflective surface could focus sunlight onto one small solar cell, concentrating the power of the sun like a magnifying glass. So he had a parabola-shaped bowl made for him in pottery class and then ingeniously lined it with a reflective bag from a box of wine.
I put those two items together and produced a solar concentrator. We produced several hundred times more power out of that cell. And at that moment, I knew we're onto something.
Briefly, it seemed John had found the perfect way to capture the sun's energy. But he'd overlooked one thing.
Unfortunately, about 10 seconds later, the cell fell to pieces because of the very high intensity and the heat. It reached several hundred degrees.
To overcome this, John developed a way to protect the cells from overheating, a system he still uses today.
Normally, we'd expose these to 750 suns of intensity, and what we have to do is have a module that is that tough it can stand a blowtorch. It's the equivalent of 750 suns of intensity.
The apparatus keeps the solar module cool even when blasted with heat intense enough to melt steel. The secret system involves pumping high-pressure water through the back of the panel.
Stone cold. That shows how effective the cooling is, and it's stone cold.
With the heat problem solved, John scaled up his idea into bigger and bigger dishes. Eventually, he found a system that could focus even more sunlight. At RayGen's pilot plant in Bendigo, Victoria, instead of focusing sunlight with a parabolic dish, they used giant mirrors. These reflect sunlight onto solar modules at the top of 3 tall towers.
What we do is we put an array of these modules into a large receiver that has a field of mirrors that focus a massive beam of light to that receiver, where we can produce megawatts of electricity out of that array of modules.
The receivers are exposed to 750 times more sunlight than they would be on their own, and this allows another major technological advance. Their solar modules consist not of normal solar cells, which turn around 20% of sunlight into electricity, but of a special type called multi-junction cells, which produce far more power.
This is the flash test that we're about to demonstrate, and this measures the power and the performance of the module. So we take a module and we place it into the chamber. This machine simulates the sun. We have a flash gun at the top, which provides the highly intense light. We simply run the process, and the machine collects the vital information about the module. So the main indicators being the power at 2.27 kilowatts, the efficiency of an astonishing 36.9%.
Multi-junction cells can turn around 40% of the sun's energy to electricity, nearly double what conventional ones achieve. This is because sunshine consists of many different wavelengths or colors of light. Standard solar cells have one pair of silicon layers, which can only absorb a small range of those wavelengths. The rest is wasted. Multi-junction cells, on the other hand, have several pairs of layers, each made of different materials that can absorb different wavelengths. So more of the sun's power is harvested. Although multi-junction cells are around twice as efficient, their price is also higher. So they're normally only used to power specialist equipment like space satellites. But by concentrating the sunshine, RayGen only need a small number to capture a vast amount of light.
The trick that we have is, yes, we pay 100 times more per square centimetre for the cell, but we get 1,500 times more power out of the cell in our system.
When the sun is focused on them, just 2 of these can produce as much electricity as 20 full-size solar panels covering the roof of a large house. John has plans to scale up his pilot plant to produce gigawatts of power. And they can even share the land it's on with others.
All we can do is spread the collectors out a little bit, which makes the system very efficient, but it allows the grass to grow and we can actually run stock at the same time. So you've got a solar farm and you've got an agricultural farm running on the same land. The beauty of a light footprint.
RayGen hope to disrupt the industry with their radical approach, harnessing even more of the plentiful power we receive from the sun. But despite its success, solar energy currently has a major drawback. Demand for power surges in the evening, just as the sun is setting. Unlike fossil fuel power stations, most solar farms can only produce electricity when the sun is shining. In the arid Atacama Desert in Chile, a major new development is aimed at solving the dilemma. Cerro de Minador. Like the RayGen plant in Australia, Cerro de Minador has a tower surrounded by mirrors that will track the sun and collect its energy. But the system works in a fundamentally different way and on a far bigger scale. Once complete, the tower will rise as high as a 70-story skyscraper. Francisco Vizcaíno is project director of this groundbreaking venture.
It is very important to develop projects like this because if we really want to turn page on the fossil fuels, we need to create green energy, renewable energy that is able to work 24 hours in the night. When the electricity is really needed in the evening and you turn on your light, this is what we need.
Cerro de Minador is designed to produce solar electricity 24 hours a day and more of it than anywhere else in the world. Northern Chile is the perfect place for this kind of solar installation, as the Atacama Desert is the driest place on Earth outside the poles. That causes the solar radiation here to be uniquely intense.
In Chile, the sun is much more powerful than any other place in the world, not only because of the power of the sun, which is strong, also because there is not water in the environment, it's very dry. So the light is coming directly to the ground without any reflection on the water in the environment. Even if the temperatures are not very high, the power that we are receiving from the sun is tremendous.
But there's a price to pay for choosing the sunniest spot on Earth. Firstly, it's also one of the windiest spots, meaning the mirrors need frequent cleaning from dust. And secondly, Chile sits in one of the planet's most seismically active zones and holds the record for the world's most powerful earthquake.
One of the most challenging things by constructing this kind of plants in the desert with this big tower is the earthquakes. The seismic movements, we need to control it by doing a special design and a special engineering and a special construction.
For the 820-foot high tower to be quake-proof, its foundations must be 24 feet deep. Once the main structure was complete, an enormous receiver was assembled for the top. This is where the sunlight will be reflected onto. But the 72-hour-long procedure to lift it into place had never been attempted before.
Lifting up this equipment was one of the biggest engineering and construction maneuvers in South America all time. It was one of the most tense moments in our life in construction. We have been lifting the receiver, taking care of the earthquakes and the wind, and it was a very, very difficult maneuver. By lifting 3,000 tons equipment from the ground 250 meters to the top of the tower was challenging, was difficult, but was very nice.
The receiver, which weighs as much as a Navy frigate, was lifted by 16 powerful hydraulic jacks. For safety, it had to be moved no faster than 16 feet per hour. After 3 days, the receiver reached the top and was successfully fixed in place. Once complete, the tower became the second tallest man-made structure in Chile and the 5th highest on the continent. As well as building the giant tower, the workers have a huge job assembling and calibrating over 10,000 giant mechanical mirrors called heliostats, spread over an area of 1,700 acres. Each one is the size of a helipad and can tilt in any direction. Today, the team in the control room are calibrating the heliostats.
Hoy día es un día muy importante porque nos encontramos ya prácticamente en la fase fuerte, la fase más activa de la puesta en marcha. Hoy día, cosas que pueden salir mal.
Jose Ramiro is the solar field commissioning manager. He must ensure that every heliostat can eventually reflect the sun's radiation accurately onto the receiver at the top of the tower. But as the sun moves through the sky, the heliostats must also move to keep the reflected sunbeam trained on exactly the right spot. If they're even a fraction of a degree out of position, the whole system could fail.
Aquí este sistema lo que nos da es la imagen del espejo concreto que estamos calibrando. En el día de hoy estamos controlando uno por uno.
For each heliostat to be able to automatically track the sun, the team must first train the reflected beam of light onto a target on the tower.
En estas imágenes tenemos las dianas que se encuentran en la parte superior de la torre, justo debajo del receptor. Nosotros procuramos siempre la mancha reflejada quede lo más centrada posible.
Once the light spot has been locked into position, the system will be able to find the black receiver automatically. One down, 10,599 to go. The best view of the heliostat field is from the top of the central tower. To get there takes a 13-minute ride in an elevator.
Here we are on the top of the tower, 220 meters, and here you see all the solar field with the 10,600 mirrors, which will be reflecting the light of the sun to the top of this tower, just where we are right now. It's very, very nice when in the morning they wake up and like sunflowers they are following the sun and aiming the light of the sun to the top of the receiver.
From here, you can see the big difference between this site and conventional solar power plants. There are no solar panels anywhere. At Cerro de Minador, they will generate electricity a completely different way. A special liquid made from salt is pumped to the receiver at the top of the tower. Here, the reflected heat from the sun raises the liquid's temperature to a whopping 1,040 degrees Fahrenheit, as hot as lava. That molten salt is then pumped back down the tower, where it's used to heat water and make high-pressure steam. That steam drives a turbine and makes electricity. Cerro de Minador is not the first solar plant to generate electricity this way, but it aims to be one of the first to produce power reliably on demand 24 hours a day. Conventional batteries are much too expensive to use on this scale. So to generate electricity through the night, Cerro de Minador has two giant storage tanks at the bottom of the tower.
Here we have the tanks. The salt today is here, melted. 46,000 tons of salt inside those tanks waiting for being pumped to the top of the tower.
The salt from a nearby mine in northern Chile consists of sodium and potassium nitrates, which have the ideal properties to store heat safely and reliably. Once on site, the salt was melted. Then the liquid was stored in a tank. Despite being 600 degrees Fahrenheit, this is known as the cold tank.
In the morning, we have all the salt there in the cold tank. 46,000 tons of salt there. During the day, the salt is being pumped to the top of the receiver, to the top of the tower. In the receiver, we heat the salt, and we start to fill the hot tank. So during the day, the cold tank is getting empty, and the hot tank is getting full.
In the hot tank, the salt is stored at 1,040 degrees Fahrenheit. The tanks are so well insulated that the temperature only drops 1 degree per day.
During the full night, we are using that salt to generate steam, and at the end of the night, again, we have the cold tank completely full of salt, and this is the full battery cycle that allows us to keep generation 24 hours using 100% only renewable energy, the light from the sun.
Solar tower technology with molten salt tanks can generate solar electricity on demand 24/7. But they only work efficiently in countries with intense sunlight near the equator. If power from the sun is to truly replace fossil fuels, we need solar-generated electricity available day and night, everywhere. team at the US Naval Research Laboratory is working on a way to supply solar power to any place, any time. It's called space solar, and it sounds like something from a science fiction movie.
The idea of space solar is that instead of collecting sunlight on the ground using a solar panel the way we usually do it, is we take that solar panel instead and put it in space and then send it to where you need it on Earth. We kind of take it for granted now that we can go anywhere on this planet and take out your phone and it tells you where you are. And we can do that because we have a system of satellites, the Global Positioning Satellites, which was also created here at the Naval Research Laboratory. And we're talking about doing the same thing for energy. Imagine if you could just go anywhere on Earth and you wouldn't have to worry about charging your batteries or where you're going to plug in, and just have energy no matter where you are.
Dr. Paul Jaffe is the lead engineer on the project. In 2019, his team set out to demonstrate a vital part of the technology at one of the world's biggest marine testing facilities. A prototype system to transfer power over long distances without using wires. Instead, the power will be sent as a laser beam.
So we have here today a 2 kilowatt laser transmitter, and we have a receiver that is made out of photovoltaics, similar to what you would find in a solar panel. And this is really a remarkable capability that unlocks all kinds of amazing possibilities. So the power beam itself is invisible and completely silent. The way that we can help show where it is with this $20,000 infrared imager. You can see the transmitter sending the beam over 325 meters to the receiver at this end of the basin, which converts that back to electricity for us to use. You'll notice, though, that you cannot see the beam if you just look without an imager.
The aim is to ultimately use a scaled-up version to send beams of solar energy collected in space back to Earth. The transmitter would be on a satellite, with the receiver down on the Earth's surface.
Imagine if we could take the boundless sunlight and space, send it effectively to the ground, wherever we need it, whether it's a refugee camp, whether it's a developing country, places that are difficult and expensive to get energy to today. If we could do that in an effective way, it would be truly revolutionary.
But firing a giant laser beam at Earth from space might naturally cause alarm. So Paul's team have developed a safety mechanism and are testing it out today. The system should detect when something or someone enters the beam and instantly shut down. This solar circuit breaker means the technology could be used on a much bigger scale in the future. For now, though, Paul's team are happy to use the beamed electricity to make a simple cup of joe.
This demonstration has exceeded our expectations many times over. We are opening people's eyes to the prospect for this revolutionary technology.
As well as creating safe power beams, Paul's team have been working for 10 years on a prototype space solar module called PRAM. Its job is to generate solar power and convert it to a form of energy that could be beamed to Earth. To check that the module would work outside the atmosphere, the team simulated space inside the lab. Liquid nitrogen matched the extreme cold. A vacuum chamber removed the air, while xenon lamps mimicked the intense sunlight. But although space conditions are harsh, there's more energy available to harness.
In space, it's always daytime and it's always brighter than anywhere on Earth. So you not only have 24-hour-a-day sunlight, but it is also brighter. You never have to worry about clouds or nighttime or rain or anything that would interfere with the collection of solar energy.
The next step was space itself.
T-minus 3, 2, 1, and liftoff.
After more than a decade's work, in May 2020, the module launched aboard the US Air Force X-37B orbital test vehicle.
It almost felt surreal to think of how it started as just like a kind of crazy idea that we proposed and got the funding and resources and support to build, and finally made it to a point where we're actually launching it into space and it's operating on orbit and it's sending us data that we're now going to use to continue to push this technology forward.
Paul's team are laying the groundwork for a potential energy revolution in years to come. In the meantime, other solar technologies are already powering ahead. Solar towers capable of generating electricity 24 hours a day are appearing in sunny countries around the world. From Israel to South Africa. While advances in technology capture more and more of the sun's energy. In Australia, RayGen plan to start harnessing the heat from their cooling system to produce another critical resource alongside electricity.
That byproduct heat can be used to desalinate water very cheaply. And that produces the two most important resources that any community needs, power and water. With power and water, you can do anything.
Lightyear have plans for a car that's so cheap to run that billions of drivers would choose solar-powered transportation.
That became the mission of the company, clean mobility for everyone. That's what we're working towards. And first by making, unfortunately, a rather expensive car to test the technology to show everybody that this is working. And then the next step is to make it available to everyone to fulfill the mission.
And the spread of solar panels from land onto lakes and oceans is opening up an almost limitless opportunity to generate clean electricity from the sun.
I'm very optimistic. I think technology can provide the solutions, that we can develop this and that we can make this transition. It's doable and the technology is almost there.
When it comes to solar, the future looks bright.